Hello everyone, differential equations, day number 1. Today we're going to talk about differential equations. We're going to talk a little bit about slope fields, something that's called an isocline or a nullcline, and visualizing solutions to differential equations. So let's get started. Okay, a differential equation is an equation that relates one or more functions and its derivatives. So an example below here would be y double prime minus 3y prime plus 2y is equal to 0. Now this is considered a second order differential equation. Second order differential equation, and the reason why is because I've got the second derivative of y involved as the highest order derivative. Okay, so let's look at this example and determine what it is it's asking us to do. It's asking us to verify that the equation y equals e to the 2x is a solution to a differential equation. So what I want to do is I want to verify that this equation is satisfied by y equals e to the 2x. So if y equals e to the 2x, then that means y prime with respect to x would be 2e to the 2x. And that would mean that y double prime, which is the second derivative of y with respect to x, would be 4e to the 2x. So if y equals e to the 2x is a solution to this, then I should be able to substitute in these equivalent values or expressions for y, y prime, and y double prime, and see that it makes this equation equal to 0. So I would have 4e to the 2x inserted in for y double prime. I would have minus 3y prime. Y prime was 2e to the 2x plus 2 times y. And of course, y was equal to e to the 2x. If the equation, differential equation, is satisfied, then we should get that the left side reduces down to 0. Okay, so let's look at this. We've got 4e to the 2x's. I've got 2e to the 2x's, so that would be 6e to the 2x's minus 3 times 2e to the 2x's, which would again be 6e to the 2x. Therefore, we have shown that e to the 2x is a solution to the differential equation. Now that does not mean it's the only solution to the differential equation. It just means it is a solution. So a solution to a differential equation is a function. That's the cool part. We're not looking for a value, right? We're looking for a function. As noted below here, you can see that we're going to just work with first order differential equations only in this course. If you're looking to get into some higher level stuff with differential equations, you can check out the linear algebra differential equations course offered after this class next year. So let's continue and look a little bit more deeper, more deeper, I don't know why I would say that, into this idea of differential equations. All right, within the idea of differential equations is this concept called a slope field. Now, a slope field is a nice way to visually represent a family of solutions to a differential equation. So as mentioned on the previous slide, there is no one function that is a solution to a differential equation, typically. Typically, there is a family of functions that are provided within a solution set. All right, so that solution set can be visualized using what's called a slope field. So let's sketch a slope field for the following differential equations. Let's say dy dx equals x plus y. So if I pick a value, let's go here at x equals 0. And then I'll go at each of these subsequent values of y. Y equals 2, y equals 1, y equals 0, y equals negative 1, and y equals negative 2. And I'm going to plot little slopes, just little hash marks that will represent approximate slope values along the line x equals 0 at each of these y values. Oh, you know what's bothering me? It's probably bothering you too. That y is different than all the other y's. Let's make that, let's clean that up. Okay, so I'm going to take x plus y in each of the cases. So 0 plus 2, it's going to be a slope of 2. 0 plus 1, it's going to be a slope of 1. 0 plus 0, it's 0. 0 plus negative 1, negative 1. 0 plus negative 2, negative 2. So whatever the solution is to the differential equation, it would have a slope of each of those at that point. Okay, so now let's look at x equals 1. Let's add x equals 1 to each of these y values. So I'd have a slope of 3 here, 2, 1, 0, negative 1. Okay, you'll start to see a pattern showing up here. But let's continue. Let's go x equals 2. Okay, so I'd have a slope of 4, 3, 2, 1, 0. Okay, you might start to see the pattern. Check out, at this point, we see a slope of 1, 1, 1, probably going to be a 1. And we can extend it the other direction as well. That's actually called an isocline. It's cool. We'll talk about that in a minute. Okay, I see a slope of 0, 0, 0, 0, 0. Okay, I see a slope of negative 1, negative 1, negative 1, negative 1, negative 1. You can confirm these by adding the x values at each of those points. And then I'm going to see other values, right? Negative 2, negative 2, negative 2, negative 2. I would anticipate a negative 3, negative 3, negative 3. Okay, and then a negative 4, negative 4. Let's confirm that this spot right here, just so that you can see and trust that I'm not leading you astray, that slope right there in purple would be a negative 5. So this would be the value x equals negative 3 and y equals negative 2, which would be negative 5. Okay, so I'm going to complete my slope field here. At the point 3, negative 1, that would be a 2. That would be a 3, that would be a 4, that would be a 5. Okay, so a solution curve. What would a solution curve look like? Let me sketch it here in a different color. Guess I could go orange. Okay, so let's say that a function had an initial condition, right? A condition that we knew to be whatever that is, 2, 1. All right, a general sketch of the solution curve would probably look like this. So that would be one of the possible solutions, right? This would be a possible solution to the differential equation. I could do others, right? Let's say that this is the initial condition, right? That's a known point on the curve. Well, I would have a curve that kind of fits this family and goes up like that, right? So it's going to produce an infinite number of solutions, which come in the form of functions, right? All right, so let's look at y prime, different notation, same concept, dy dx, y prime, y minus x. So why don't you pause the video and I'll complete it off screen. Okay, I've drawn the slope field for y prime equals y minus x. It looks like we've got some kind of oblique asymptote here. I could sketch a solution curve. Would look probably something like this. Okay, there's one of our solution curves. We could draw many of them, okay? But this is the process of slope fields. It helps us to visualize the family of possible solutions to a differential equation. Let's continue with a couple more down below. Okay, dy dx equals cosine x. Okay, so what you're going to want to do here, this is unique, okay, but I'm going to just consider, because this differential equation is not dependent on y at all, it's only dependent on x, I'm going to put x equals 0, and then I'm going to go out here and do x equals, let's go pi over 2, maybe I'll squeeze that in a little bit further. Let's do that. X equals pi over 2, and then x equals pi, and then x equals 3 pi over 2. Okay, so at x equals 0, what's cosine? Well, cosine of 0 is 1. Okay, so 1, that's going to be the slope of the curve at x equals 0. How about cosine of pi over 2? Well, cosine of pi over 2 is 0. Cosine at pi, negative 1. Cosine at 3 pi over 2 is 0 again. Okay, I could go the other way. You're going to see that I'll get 0 here at negative pi over 2. And I'll get 0 at negative 3 pi over 2. And I'll get a positive 1, excuse me, a negative 1 at negative pi. Okay, so what does my function look like? Well, let's sketch one, potentially, right? Let's say that one value, one output of the solution, right? Y of 0 is 0. Well, that would make the function look kind of like this. Well, what does that look like? That to me looks like y equals sine x, right? Or some version of it, right? Plus c, right? I could shift that up and down. Okay, so think about this now logically. If dy dx equals cosine x, that means that the derivative of y with respect to x is cosine. What's the derivative of sine? Well, it's cosine. Right? Now, the family of functions, the way that that exists is potentially that there's some kind of vertical shift going on here with the sine function. Oops, I didn't sketch that second half very well. Okay, there's a vertical shift. So the family of functions here is based on the initial condition. So the sine graph could be shifted up or down, left or right, whatever. Okay, now let's consider y prime equal to sine x. And let's just think about what function's derivative gives us sine x. Well, that would be negative cosine x. Okay, so we should visualize y equal to negative cosine x as a family of solutions, right? Plus c. I don't know what my initial condition will be, but let's graph sine x. So at x equals 0, sine is 0. At x equals pi over, excuse me, let's go pi. It's going to be 0 again. Right, at x equals negative pi, 0. Right, those are all sine outputs. Sine at negative pi, sine at 0, sine at pi, all equal to 0. So we're sketching slopes. What's the sine? Oops, sine at x equals pi over 2. It's going to be 1. Sine at x equals 3 pi over 2 is negative 1. Okay, and then likewise on the other side, you'll see symmetrical outputs for these slopes. So if I were to graph, let's put an initial condition on this. Let's go right here. And when we sketch, we're going to see that that's cosine shifted downward, right, and flipped over and shifted downward. Now, if I would have centered it on the origin, right, or had the typical max and min values at negative 1 and 1, we would see that that would be a reflection of cosine. Okay, so that's how you can visualize a family of solutions for a differential equation using a slope field. Let's continue on the next slide with a few examples. Okay, so drawing slope fields is all well and good. It can get annoying when you're doing small calculations with 1 minus a negative 1, and then you screw something up, right? So the Greeks had a word for same called isocline. Okay, an isocline for a family of solutions to a differential equation is formed by the set of points in which some member attains a non-zero constant slope. I'll explain below. A nullcline for a family of solutions to a differential equation is formed by the set of all points in which some member attains a slope of 0. So instead of using our methods from earlier where we drew out all of those little hash marks or slopes by using simple addition and subtraction, which we had to do, 25 to 30 times, what I'm going to do is I'm going to isolate and determine isoclines. So if I want to know where dy dx equals 0, I'm going to set the derivative equal to 0. And I'm going to solve for y. Well, y would equal x. What that means is that along the curve, the isocline y equals x, our slope is equal to 0. So where would the line y equals x be? Well, it would be here. So I'm going to put slopes of 0 along this isocline y equals x. dy dx equals 0. Okay, let's look at another isocline. Let's determine the isocline dy dx equals 1. Okay, so where would the slope on this family of curves be equal to 1? Well, again, we take and we set 1 equal to x minus y, and we solve for y. That'll be the equation y equals x minus 1. So at x minus 1, we're going to get a slope of 1. So along that isocline, y equals x minus 1, I know that y prime is equal to 1. You can see where I'm going with this. Of course, you'll notice that if I were to, then go with dy dx is equal to 2, I set that equal to 2, x minus y, so y would equal x minus 2. Okay, so you're going to see that I'll have a slope of 2, boom, 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 and then you start to see the pattern, right? Our next tier of derivatives would be dy dx equals 3, and then dy dx equals 4, and then dy dx equals 5. And we can go the same in the opposite direction. Okay, why don't you fill in the rest of both the slope field for dy dx equals x minus y and dy dx equals 2x. Okay, let me show you a couple tips and tricks here. You can see slopes of 0, 1, 2, 3, 4, 5. So back here would be -1, -2, -3, -4, -5 along those isoclines. Now the isoclines for dy dx equals 2x. If x equals 0, the slope equals 0. Therefore, along the vertical line x equals 0, slopes are 0. If you were to say, where is this equal to 1? Right, you would get where x equals 1/2. I don't have an x equals 1/2, so if this is x equals 1, we would get slopes of 2. If this is x equals 2, we'd get slopes of 4. If we get x equals 3, they would be slopes of, slope equal to 3, we would get slopes of 6, and then -2, -4, -6. Now, I do want to look at this function right here. Let's say an initial condition here was the point 0, -3. What does this look like to you? Right, that probably to you looks like x squared, and you're absolutely right. If I took the derivative of y equals x squared minus 3, I would get dy dx is equal to 2x. Look at that. So the solution curve, this solution is a curve, right? And the curve is y equals x squared minus 3. It's a solution to dy dx equals 2x. All right, let's look at one more slide. Oh, you know what? No, that's it. That's it for today. Using isoclines, of course, that are slopes not equal to 0, nullclines, which are slopes equal to 0, we can determine slope fields and see families of solutions to differential equations. All right, guys, we'll see you in the next video. Have a great day.